Welcome to this video on vertical kinematics, where we explore a rock being tossed into the air and falling over a ledge into a river below. A person is standing on a riverbank and throws a rock upwards with a velocity of 15 meters per second. They do not catch it on the way down, it falls into the river. If the river is 2.2 meters below where the person releases the rock, A, what is the maximum height reached by the rock relative to the river? B, what is the rock's velocity at the moment it hits the water? And C, how long does it take before the rock hits the water? Before we can find the maximum height reached by the rock relative to the river, we need to list our variables down the left and draw a diagram on the right. So we know that a rock has an initial upwards velocity of 15 meters per second, so VI is equal to 15 meters per second, and it's upwards, so it's positive. The river is 2.2 meters below where the person releases the rock. So from the person's hand here to the river is a displacement of, and it's negative 2.2 meters because it's downwards. Because it's not otherwise stated in the question, we can assume it's happening on Earth. So we know we have an acceleration due to gravity equal to negative 9.81 meters per second squared, negative because gravity goes downwards. Now, specifically in part A, we're asked what is the maximum height reached by the rock relative to the river? Well, we're going to find the maximum height reached relative to the hand and then add this displacement to that relative to the river. So the max is equal to question mark. And we can just finish this diagram up by adding the last couple things we're going to find, but we don't have. So eventually we're going to find the impact velocity, so the velocity final here, and the time of this entire motion up and down. Now we're ready to sort out the variables we have and we need for part A. Projectile questions are unique because you don't always need all the variables, and you have to be careful because some of the variables apply in certain situations only. We start with what we know we have. We have a VI upwards at 15 meters per second. We know we have acceleration due to gravity equal to negative 9.81 meters per second squared because it's downwards. We're looking for our displacement max in part A, which is this displacement upwards, so we can add it to the displacement from the river. We don't know the time that it takes to get upwards. And now for the most important part of this question, the VF is actually equal to 0 meters per second because at the very top here, so at the top, velocity final is equal to 0 meters per second. The ball's not moving upwards or downwards at the very top. So in part A, we're not going to solve the entire question. We're just going to solve this small segment where the ball is launched at 15 meters per second and comes to a stop at the top. And we're going to find this D max here. We're now ready to pick our kinematic equation. So the variable we're looking for in part A is our D max here. So we're looking for an equation that has VI, A, D, and VF. We don't have, and we're not looking for the time. So we can eliminate all the equations that have time in them. And this leaves us with this kinematic equation right here. So we'll write it at the top. VF squared is equal to VI squared plus 2 times the acceleration multiplied by the displacement. And now we're ready for some numbers. So our VF, as discussed, is 0 meters per second at the very top. This is equal to our VI, which is equal to 15.0 meters per second. And this whole term is squared, plus 2 times multiplied by our gravity, which is negative 9.81 meters per second squared, multiplied by our D, which is our D max, which is what we're looking for. So multiplied by D. We'll call it M for D max. So we can start by squaring our 15 here, and that gives us 225 meters squared per second squared, plus 2 times negative 9.81 is equal to negative 19.62 meters per second squared, and this is still multiplied by our D max and still equal to 0. We want to get the term with our d max all alone, so we subtract 225 meters squared per second squared from both sides. So on this side, it just cancels because 225 minus 225 is 0. And on this side, we're left with negative 225 meters squared per second squared is equal to negative 19.62 meters per second squared multiplied by our d max. And lastly, to get our d max all alone, it's being multiplied by negative 19.62, so we have to apply the opposite. So we divide both sides by 19.62 meters per second squared. So 19.62 divided by negative 19.62 is just 1, so this disappears and leaves us with our d max equal to 225 divided by 19.62 equals 11.5 meters. So our maximum height reached relative to where the ball is released is 11.5 meters. But don't forget, we're asked for the maximum height reached by the rock relative to the river, not the hand. So to find this, to find our height max, we have to add our displacement from our hand to the top where the ball stops moving, so our dm, plus the displacement from the river to the hand, so we'll just call it river to hand, and we fill in these numbers quickly. We have h max, so our max height is equal to our dm, which we found here, 11.5 meters, plus our displacement from the river to the hand, which is 2.2 meters, giving us a height max equal to 13.7 meters. We're now ready to move on to part B, but before we do that, let's clean up our variables and our diagram a little bit. Because I like to use variables that are given in the question rather than calculated variables, I've moved the variables we found in part A to the bottom here. You'll notice I've also removed them from the diagram to make things less convoluted. So all I have left in the diagram is the information we're given in the question, our VI of 15 meters per second upwards, gravity downwards, our displacement here from the original position of the ball to the river, and our VF, which is the velocity the ball hits the water at. We still have our time here as well, which we don't have. So let's go ahead and add our displacement to our list of variables now. So our displacement is negative 2.20 meters. So this is how far the ball is displaced from its starting position. So initially the ball goes up, reaches its maximum displacement here of 11.5 meters from its starting position, and then it comes back down. Here its displacement is 0, and then it goes down another 2.2 meters for a final displacement of minus 2.2 meters. So now that we've cleaned up our diagram and we've cleaned up our variables, we're ready to find the rock's velocity at the moment it hits the water. So we're looking for VF here. And we have 3 variables and just our unknown, so we can immediately jump to picking our kinematic equation. For part B, we have our VI, we have our acceleration, we have our displacement, and we are looking for our VF. We don't have, we're not looking for our time t, so we can cross out all the kinematic equations that have t in them. And that leaves us with just this one. So this is the kinematic equation we'll use to solve part B. We'll write it up top here. VF squared is equal to VI squared plus 2 multiplied by the acceleration multiplied by the displacement. We're ready to add some numbers. VF is what we're looking for, so VF squared is equal to VI squared, which is 15 meters per second. And this is squared plus 2 multiplied by the value of gravity, which is negative 9.81 meters per second squared, multiplied by the displacement, which is negative 2.20 meters. So we still have our VF squared here. It's equal to 15 squared, so 15 squared is 225. So 225, and it also squares our units, so meters squared per second squared, plus 2 multiplied by negative 9.81 multiplied by negative 2.20, and this equals positive 43.164. Our meters times meters makes meters squared, and we have just seconds squared on the bottom, so we end up with meters squared per second squared. We'll keep a few extra decimal points so we can avoid any rounding errors. Completing this addition, 225 plus 43.164 gives us 268.164 meters squared per second squared, and this is equal to our velocity final squared. To finish this question and get just velocity final, we need to take the square root of both sides. So my square root and my squared leave me with just my velocity final, and this is equal to the square root of 268.164, which is positive or negative 16.4 meters per second. Although when we take the square root of a number, we end up with both a positive and a negative solution. In physics, only one of these is correct, so we have to look at our actual problem. We've defined up as positive and down as negative. When the ball hits the water, it's going downwards. So that means our final velocity is negative 16.4 meters per second. We add this value to our list of variables, so negative 16.4 meters per second. And we're now ready for part C. In part C, we're asked, how long does it take before the rock hits the water? We have 4 variables that we have a value for and only one unknown, so we're definitely ready to look right at our kinematic equations. As we have 4 variables and only one unknown, we can actually use any of the kinematic equations that has the t we're looking for in it. So this equation here doesn't have t in it, so it won't help us. And as you probably know, I don't like to use values that I've previously calculated in future calculations if I don't have to, because in case this has a mistake in it, that means I'm going to propagate my error through my next calculation. So if we're not using VF, that means we also can't use this equation and we can't use this equation. So it leaves us just this equation to solve for t. So let's write this at the top here. The displacement is equal to the velocity initial multiplied by the time plus 1/2 multiplied by the acceleration multiplied by time squared. Let me be fully transparent about using this equation before we move forwards, because it's probably not the easiest equation to solve. Our VI is not equal to 0, it's equal to 15. That means this t term here will stay, and we also have a t squared term. So because we're looking for t, this is actually going to create a quadratic equation that we're going to have to use the quadratic formula to solve, or an online quadratic solver. Now, if we were to use an equation with VF in it, like this one or this one, we'd avoid this problem completely and the algebra becomes more straightforward. So after I solve this using the quadratic formula, I'll quickly show you the solved version of an equation with VF in case that is the safer route for you. We're ready to add our numbers. So our displacement is equal to negative 2.20 meters. Our VI is 15 meters per second, and this is multiplied by our t term, plus 1/2 multiplied by our acceleration, which is gravity, negative 9.81 meters per second squared, multiplied by our t squared term. 1/2 multiplied by negative 9.81 gives us negative 4.905 meters per second squared, and this is still multiplied by our t squared term, plus 15.0 meters per second multiplied by t is equal to negative 2.20 meters. To get this ready to use the quadratic formula, we want to set it equal to 0. So to get this 2.2 to the other side, we add 2.20 meters to both sides. So on this side, our negative 2.2 and our positive 2.2 cancel out, so it leaves us with 0 is equal to, I'm going to rearrange these terms quickly, putting the t squared term first, so is equal to negative 4.905 meters per second squared, multiplied by our t squared, plus 15.0 meters per second t, plus 2.20 meters. In our quadratic formula here, this here is our A term, this here is our B term, and this here is our C term. So we can put in our numbers for our A, B, and C's and solve for our roots of this quadratic equation. So adding our A, B, and C values to the quadratic formula, we end up with this here. And if we solve this, we end up with two different roots because of the plus and minus here. So our two roots for t end up being t is equal to 3.20 seconds, and t is equal to negative 0.140 seconds. Let me just solve this quickly as an aside so that those of us who aren't comfortable with this can see how it's done. To solve a quadratic, I use the quadratic formula, and I take my A, B, and C terms and I put them into the quadratic formula in their respective places. I then end up with this, and I usually start with the values in the square root, but really you just need to work through the math and it doesn't matter where you start. So 15 squared gives me 225, and then negative 4 times negative 4.905 times 2.2 gives me 43.164. I also quickly do this multiplication on the bottom here. 2 times negative 4.905 gives me negative 9.81. I then sum my numbers in the square root. So 225 plus 43.164 gives me 268.164. I then actually take the square root, so we're just dealing with numbers. So the square root of 268.164 gives me 16.3757. Now we just solve our two different scenarios. So in our first scenario, we're adding here. So negative 15 plus 16.3757, that gives me this top root up here, where we get 1.3757 on top. We divide it by negative 9.81, and we end up with our first root for time here of negative 0.140. If we subtract here, we go negative 15, subtract 16.3757. That gives me my second root here. So the top becomes negative 31.3757. We divide that by negative 9.81, and we end up with our second root for time of 3.20. So that's where the roots come from. We know there can't be two different times. There can only be one answer for this question, so the logical answer is the positive time, because negative time doesn't make sense. However, for those of you that are mathematically inclined, I'll explain where this negative root comes from. If you were to backwards project the ball here until it hit the river on the person's side here, essentially going through the cliff to the river here, that would have happened at a time of negative 0.140 seconds. So this part here doesn't exist, but technically this is a parabola that we're solving the roots for. So if we were to complete this parabola backwards into time, we'd end up here at negative 0.140 seconds. You may be concerned if you use the quadratic equation, will there ever be two numbers that are hard to decide between? And the answer generally is no. One of them will often be negative or very, very small. So small that it doesn't make sense is the answer. So usually it's pretty straightforward to pick which t or which root is correct. Now there are circumstances where they can be close and you'll have to spend some time thinking about what's actually happening in the problem to pick the right root. Let's just add this time to the side here so we have it for confirmation when I solve for the time using VF instead as I promised. So our time is equal to 3.20 seconds. As promised, I'll now show you the solution for C using a kinematic equation that has VF in it. So when choosing your kinematic equation to solve with VF, you'll notice there's two options. We have our d is equal to VF plus VI over 2 multiplied by t, or VF is equal to VI plus AT. I'm only going to solve one of the ways, and if you want to also solve this problem using this equation to confirm our answer a third time, you're welcome to. So here I just put in my values for my d, negative 2.20 meters. I put in my value for my VF, and I use the unrounded value just to make sure we didn't create any rounding errors. I added the two numbers, and I got negative 1.3757. I divided this by 2, and I got negative 0.68785. To get the t all alone, I divided both sides by this negative 0.68785, and this gave me a t of 3.20 seconds, confirming what we got using the quadratic equation. If you're doing questions for practice and you're not very comfortable with the quadratic equation, I would suggest that method just so you start to get more comfortable with it. That being said, if you're on a test or a quiz, I would stick to what you're most comfortable with. Now, if you ever find yourself with a little extra time, it's always great to solve the problems multiple ways and confirm your answer. Thank you for watching this video on vertical kinematics, where we analyze the rock being thrown into the air over a ledge into a river.